Electrolytes are necessary and indispensable in all electrochemical devices, with their fundamental function remaining independent of the chemical composition and application of these devices. In this sense, the role of electrolytes in electrolytic cells, capacitors, fuel cells or batteries remains consistent. They act as a medium for charge transfer between a pair of electrodes with a charge existing in the form of ions. The vast majority of electrolytes are of the electrolyte solution type, consisting of salts dissolved in the solvent, where the solvent can be either water or organic molecules and remains in a liquid state within the operating temperature range. Due to their physical location in electrochemical devices, for example, sandwiched between the positive and negative electrodes, electrolytes interact closely with both electrodes. Hence, when the new electrode materials are introduced, compatible electrolytes are usually required. The interface between the electrolyte and the two electrodes generally determines the performance of the device. In fact, since the advent of modern electrochemistry, these charge interfaces have been a focal point of attention, as is the case with contemporary lithium-based rechargeable battery technology. In batteries, the chemical properties of the positive and negative electrodes determine the energy output, while the electrolyte in most cases determines the rate of energy release by controlling the rate of mass flow within the battery. Conceptually, the electrolyte should not undergo any net chemical changes during battery operation, and all Faradaic processes should occur within the electrodes. Thus, simply put, the electrolyte can be considered an inert component within the battery and must exhibit stability towards both the positive and negative electrode surfaces. This electrochemical stability of the electrolyte, typically achieved in practical devices through kinetics rather than thermodynamics, is particularly crucial for rechargeable battery systems, but is often challenged by the strong oxidizing and reducing nature of the cathode and anode, respectively. As the pursuit of new battery systems with higher energy density intensifies, the severity of this challenge increases, driving the exploration of more oxidizing cathodes and more reducing anodes as candidate electrode materials, thereby continually demanding enhanced electrolyte stability. For the kinetic stability of these new electrolyte-electrode interfaces, specific surface chemistry is often required. While the potential of electrode materials is typically quantified by the number of volts relative to a specific reference potential, the stability of the electrolyte can also be quantified by the voltage range between its oxidative and reductive decomposition limits, known as the electrochemical window. Clearly, the redox potentials of both electrode materials must fall within the electrochemical window to achieve rechargeable battery operation. Of course, electrochemical stability is just one of the requirements that an electrolyte must meet. An ideal electrolyte should exhibit the following characteristics. 1. It should be a good ionic conductor and electronic insulator to facilitate ion transport while keeping self-discharge to a minimum. 2. It should have a wide electrochemical window so that electrolyte degradation does not occur within the working potential range of the positive and negative electrodes. 3. It should remain inert towards other battery components such as separators, electrode substrates, and battery packaging materials. 4. It should be able to withstand various forms of abuse, including electrical, mechanical, or thermal. 5. Its composition should be environmentally friendly.